It's exactly 12 o'clock noon time, colleagues. I'd like to greet you all and welcome you to our webinar titled How PV Quality Affects Performance. Our speaker today is Dr. Jackie, an operations manager at PV Insights, and I'm Sinetemba Mnguni, your moderator for the session today, and also a technical specialist at Savia. Dr. Jackie has had a distinguished career starting with her PhD at the Nelson Mandela Metropolitan University, where she focused on photovoltaic device characterization, specifically in electroluminescence. Since then, she had quite a number of roles, including her laboratory manager role at the photovoltaics testing lab, and also served as a senior researcher at the same university, and also as part of the research group. Now as an operations manager at PV Insights, she oversees operations and maintains quality management systems, and also continues to improve the testing services offered in the facility. Her work highlights and includes developing faster and better systems and solving complex puzzles.
Spin off a separate company, the Fortress.
Can we all turn our microphones, colleagues? Thank you. Not sure where I may have lost my presentation, but I think I remember mentioning the work that she does, including the development of faster and better systems and solving complex puzzles and providing insights into factors affecting PV module quality. We're excited today to take a deep dive into the intricacies of PV quality and how it impacts performance. So let's get started, colleagues. I'd just like to hand over to Dr. Jackie to take over from here moving onwards. Thank you so much for joining us this morning. Dr. Jackie, over to you.
Yeah, thanks very much. I'm just going to take over sharing my presentation. Okay, perfect. I trust it's on the screen as we speak. Yes, no, thank you very much, Sinetemba. Thank you very much for the introduction, and thank you for the opportunity to discuss what I think is a very important matter, which is PV quality and how it affects performance. So the work that we're presenting today is done by PV Insight, and we're very grateful for the opportunity of the South African Photovoltaic Industry Association, or SAPIA, to present this work. So PV Insight, just to give an overview of the company, it is a spin-out company of Nelson Mandela University. The PV Research Group at Nelson Mandela University was very well established in the South African market as a PV research institute. And Nelson Mandela University and PV Insight are situated in Gqeberha in the Eastern Cape. And we are an accredited testing laboratory. So we have this year been celebrating 10 years of PV testing. First off, as the university founding the PV testing laboratory, which started in 2014, and later continuing as the spun-out company, PV Insight. So it all began when the physics department had a special expertise in semiconductor physics, which is the basis of all photovoltaic technology. So based on that strong background in PV research, in 2014, there was a need for photovoltaic testing to occur, because as the large plants in South Africa were being constructed. These projects had requirements for PV testing. So we started our very first project in 2014. We originally worked in the physics department basement, and then we very quickly realized that there was nowhere near enough space to handle pallets and large volumes of modules. So since 2014, we've been in space that was originally the CSIR campus on Gomery Avenue. It has since become the Ocean Science campus in Gomery Avenue in Summerstrand. So by December 2014, we had our very first large contract, which involved hundreds of modules that were being tested for power and EL. And this project was conducted in a very all hands on deck approach. We all got involved, and it was a success, and it was the start of the work of PV module quality testing at Nelson Mandela University. Subsequent to this, the process has evolved, and we've got streamlined it. So instead of just having one project a year, we're busy with multiple projects. And in 2016, the laboratory was accredited. So in 2017, PV Insight was established as a spin-out company from Nelson Mandela University. And we acquired through the university a mobile testing laboratory, which is the MBJ Mobile Testing Lab 3, which you can see in this block here, the block by 2019. Which is a great piece of equipment. It allows you to do power and EL tests and quality assessments on site. And we would still be using that equipment continuously if we hadn't had this increase in the size of PV modules, which meant in 2022, we've acquired a new mobile lab. So at the moment, we have 2 mobile labs that are fully operational. So since 2016, we've been a fully accredited SANAS laboratory. So we are the oldest operational PV module testing laboratory in South Africa. So we continue to test and reach these things. And yeah, so 2014 to 2024, we've seen 10 years of module quality and 10 years in participating in the PV module, in the PV sector in South Africa. So that was just an introduction to the company. So I hope it also gave all the latecomers a chance to join, so they don't miss more of the other content. So next slide. Even though this is a SAPVIA webinar, I think it's not a bad thing to start with the first principles of what is a PV module and how does it work. So a photovoltaic module, or a solar panel, as it is conventionally called, is made up of several solar cells. And the basic principle of a solar cell is it's an electronic device, and it directly converts sunlight into electricity. So the light's shining on the cell produces a current, and this current flows through an external circuit. So in this illustration, it can light up this light bulb. So these individual cells are then connected together to make up a module. So the modules are soldered together and connected in string and in series strings or parallel strings, depending on the required output. And then these cells are then encapsulated, and then glass is on the front surface. There's a back sheet at the back, and then you have an aluminium frame to provide structural support. On the junction box is added at the back, and then you have connections. So fundamentally, you have an incredibly robust and durable item in a PV module. And this basic module structure and the technology has changed a lot with time, but the basic ideas of the cells sandwiched between encapsulate with either glass or glass in a back sheet, and an aluminium frame is pretty standard. So I hope we can all agree that a PV module is the most important part of a PV system. Because as we've mentioned, the PV module is the part that contributes to the energy generation. So it's responsible for converting sunlight into electrical energy. The overall efficiency and the performance of the system is also dependent on the quality of the module and the condition of the PV module. Any damage or factors that are reducing the efficiency of the module, soiling or mechanical damage or defects will affect this efficiency and performance. The durability of the PV module also influences the lifetime of the entire system. So as I said before, PV modules are in themselves quite a robust and a durable product. I mean, there are very few products available which would standard be giving you a 20 or 25-year lifetime. So fundamentally, it should have a very good lifespan, and obviously that durability and that reliability is very much dependent on the quality of the module. The PV module is also one of the most expensive components of a solar power system. So choosing the right modules can have a big effect on both the initial investment and the return on the investment with time. So environmental factors, so these modules are exposed to the environment and they need to withstand conditions like UV radiation, temperature fluctuations, wind, and they need to be able to deal with quite different climatic conditions, from snow in some parts of the world to extreme dry, hot conditions in others. And the degradation that is occurred by these environmental factors also has a significant effect on the overall system's performance. So the key risks that we can look at for PV modules, and from the perspective of a PV module buying, a PV module buyer. So I'll briefly go into the first three, and then we can delve into the technical risks a bit more detail. But contractual risks mean that basically standard module supply agreements can also often be very vague about what is required on both a technical and a quality assurance basis. And without this being examined detailed, then it can limit the buyer's ability to look at the quality issues that occur. So the efforts to mitigate this can involve setting up requirements that specifically address module quality and not allowing for just a generic requirements for things like the bill of materials and providing defined ways in which modules are accepted and rejected. In the second one highlighted here, we discuss manufacturing risks. So obviously, a lot of the quality and the value of a module is determined at a factory level, both in the factory and on the production line. So the process of auditing factory is overseeing production and inspecting finished good is very vital to mitigate these manufacturing risks. So policy risks, there's a lot of dependency on international policies, international trade, and supply chain issues that can affect the procurement of PV modules. So finally, to get to the module technical risks. This encounters both quality and performance concerns. So PV modules have in themselves changed quite significantly over the past few years. And the next slide I have will speak to that. But these changes are not, because these changes in module technology have happened quite relatively fast, it is not possible to have real-world data available for these newer technologies. So this is a continuing concern. And extended reliability testing and quality testing is very important to protect buyers from unseen problems with new technologies. So this diagram very effectively sums up quite a lot of information. So that's why I have not attempted to recreate it or summarize it too much, because it comes from a very interesting journal article that I've accredited below, which is looking at the changes in PV modules and how the reliability is associated with it. So this is summarizing here the sort of three stages that have occurred in the evolution of crystalline silicon modules. So in this diagram is then focused on looking at crystalline silicon specifically, sort of giving an overview of the fact that modules that came out in 2014 are actually very different in appearance and size and technology to the modules that are currently available. So the first step has been a general increase in power. So in 2014, modules were typically 280 watts approximately, in that sort of range. And today we're looking at modules that are 500 watts plus. There are modules available that are 700 watts. So this is a dramatic change in what a single module can produce. In part, this is due to the larger size of modules. So in 2014, modules would be about 1.6 meters squared, which means they're about, 1.7 meters squared, which means they're about 1.7 meters tall and only about a meter wide or so. And today you're looking at over 2 meters, 2.3 meters tall. And this has contributed to us and all other laboratories having to actually increase and upgrade their equipment just to be able to test these newer sizes of modules and these new, because physically the test area needs to increase in order to accommodate the larger modules. The cells themselves have actually also increased in efficiency, and the cell technologies have changed, with TOPCon and silicon heterojunction cells being available now in PV modules. The other change, and this is, we can discuss this in detail in the when we look at some of the results, but the number of bus bars and interconnections have increased, which has some effects in mitigating the effects of some mechanical damage like microcracks. And also in reducing the costs and the weight and other issues, we are looking at thinner cells and thinner glass that's involved, and that potentially has issues with how these modules last in the long term. So the past 15 years has seen a dramatic reduction in the cost of PV. The graph here, which actually only goes up to 2022, but it illustrates from the past, going backwards very well, how dramatically the prices of PV modules have decreased. And the current situation in the PV module supply chain is very challenging itself, because it's been marked with a dramatic oversupply of modules, which affects both the manufacturing capacity and the factory utilization. And it means that the prices are, the prices are incredibly low at this point, meaning that many module manufacturers are actually not able to sell modules in a profit, which and sort of having reached a sort of a ceiling of how to reduce production costs, it is quite a challenging situation, as lower prices lead to this oversupply and also inability to really sell modules at a profitable rate. But that is then a global issue illustrates how our industry is very much affected by the global PV situation. Okay, so the risks of damage and defects can occur throughout the lifetime of the PV module. And damage and defects can occur in the stages, in sort of 4 defined stages. So when modules are manufactured, many defects can occur during this process. So these defects are normally detected during part of the factory's quality control process, and they can also be identified during independent audits. So independent factory audits are quite an important process in a quality control approach, and they are offered by many international consultancy firms who have quite a good experience in the factory processes, the challenges in PV module production, and are aware of the ways that these can best be evaluated and audited. So the testing that occurs at the manufacturing level is generally referred to as upstream testing, and this can also include processes like ensuring containers are packed correctly, correct batches are sent, that level of testing and auditing. So the next step then is the shipping and storage of modules. So microcracks can occur during the transport process, and things like shipping and handling and transportation of modules to site. At this point, it's very possible that damage can occur. The packing of modules is actually very much improved, and modules are packed generally in a very secure way. So barring accidents happen, there shouldn't be significant damage occurring in this process, but accidents do regularly happen, and evaluating for these microcracks that could result in more significant issues is very important. The challenge that one finds with the packing of modules is, while the packing is very well designed as a single-use option, it is single use. So apart from that being that there's environmental concerns, it also means it's very difficult to reuse. And it's once modules have been unpacked, it's very difficult to reuse that packaging to safely move them to another location or to send them for testing. So that continues to be a challenge in the transportation of modules. So the module handling process, so poor module handling or bad installation procedures can result in module damage. So these accidents will typically result in invisible damage and things like microcracks. So, and this can only be detected through additional testing. Once modules are installed and operational, any existing microcracks that might have occurred in the other stages of the process can actually get worse and increase in severity over the lifetime of the module. This means that a small crack can, with the thermal cycling of the module, affect a larger and larger area. Also, extreme weather events, things like hailstorms, high winds can also result in damage to modules. And operational activities, things like cleaning, maintenance, grass cutting around the modules can again result in damage to the module. So reliability issues are can also occur over the life module, and these are often related to the bill of materials, or what materials the module was actually made out of. So the mitigation for these steps is to look at downstream testing. And the downstream testing options we're going to discuss after we have a short hold. So I'm just going to stop sharing for a moment and hand it over to Mariska, who's going to share her screen. So I see we've already, to join the Mentimeter, you can join the link on the in the chat. You can also scan the QR code that's here on the screen. So the first question, so this is just to get everyone awake and make sure you've joined the right seminar, right webinar, but what defects or failures do you think have the biggest effect on PV module performance? So we already have some responses. Yeah, so microcracks we're going to discuss in more detail in the later slides. Everyone likes microcracks. So I mean, the accidental damage is quite a significant thing, and that can happen obviously by accident. You also have, I see, handling coming up as an option. So I think there's been significant improvements in the way that easy it is to cause cracks within the modules. And a lot of that is because we couldn't see the cracks that were being caused. So batch sheet problems also comes up here as an option. So the batch sheet is the white surface on the back of a module, and historically those can degrade in different ways. See, someone's put in snail trails. So snail trails is one of the ones one always has to make sure you explain that it's not got anything to do with snails walking over modules, but rather looking at a snail trail is actually indicative of a microcrack. So where there's a snail trail, there's a microcrack on that cell, and it becomes visible as a sort of fine silver line that appears on the cell. Great. And then I see we have put in hotspots as an option. So it is possible. So one of the techniques that we're not going to discuss in this talk, but it's a very useful quality control technique, is in an operational plant to do thermal inspection. And this is done through drone scans and identifying hotspots that can point you in the direction of defective modules or issues within that system. Okay, so yeah, I mean, human error and offloading and accidents are all sort of similar in that as soon as you move a module from one place to another, your chances of something going wrong increase. I think we're sort of running out of steam here. Let's go to the next one. So I'll give you a minute to respond to this, but in the previous slide, I put out what were the 4 stages in the lifetime of a PV module. So when do you think the most of the damage occurs in the lifetime of a PV module? So the options are during the manufacturing process, during shipping and transport, or during installation, and then in the operation. So over the 20 to 25 years of operation, the damage that can occur that then versus installation. So it seems that of the responses, we are looking at installation as being most people's concern, with shipping and transport and operation very similar. And I think that's a very important thing to note. I mean, we all see how modules can be handled, how difficult it is to always get them where they need to be if they're going on roofs or things. And unfortunately, the byproduct of these modules getting so big is also very heavy, which makes them even more challenging to move carefully. Okay, I think we've sort of got most of the answers. We can always at the end see if there's any other added into the word cloud. So thanks. I'm going to go back to the presentation. Okay, perfect. So the module warranty is generally what the first answer people say if they ask what assurance of quality do you have on a PV module. So typically, the PV module warranty is divided into two factors. There's the performance warranty, and these are two just examples that were taken off of data sheets. But basically, the warranty would be, for example, 25 years. It takes into account an initial first-year drop of 2.5% power, in some cases, from the labeled power output. And it means that the power should be no less than 97.5% at the end of the first year. Then for subsequent years, from year 2 to 25, you're looking at 0.6 or 0.7 or 0.8. It's normally in those sort of range, percentage decrease per year. So the actual output of the product has to be determined using standard test conditions only. And the testing needs to be done by a recognized third-party institute, and the measurement testing uncertainty needs to be accounted for in those measurements. So that means that the lower your measurement uncertainty in the measurements you take, that the less of a range is allowable. So the second part to this is then the product warranty. So this is ensuring that the module itself is free from defects in both the materials and in the workmanship. And this is again pinned on normal application of the module, normal installation, and normal conditions. And the time period for this product warranty varies from manufacturer to manufacturers, typically 10 to 15 years. So the risk with the warranty in itself is that the terms can be slightly ambiguous, and they can limit the buyer and how you deal with it, or what the recourse is if the modules underperform or fail in some way. And they're also very much dependent on the manufacturer's financial stability, because that is who's responsible to respond to claims. So this is a diagram that I borrowed from a webinar that I attended by a European company that basically offers, I'd say, gap insurance for module warranties. But I think it highlights it very clearly. That really the risk that you have with the warranty is pinned on two things. It's looking at the actual performance of the module or the underperformance of the module, which can be ascertained and ensured through a quality assurance process that involves all the functions of quality assurance, looking at factories, doing reliability tests, doing acceptance testing, and also looking at the actual stability and the credibility of the supplier of the module manufacturer. And so the value of the warranty from any PV module is really based on those two factors. So that is why there's a very strong need for testing to occur at all those stages that we mentioned in the PV module's lifetime. So we spoke briefly about the factory testing, the factory audits that can occur. But as we highlighted in the poll, the damage can occur during the transportation of modules and also in the installation. So it's very important to include some form of post-delivery acceptance testing. So site acceptance testing can have various forms, but typically you would want to do some form of visual inspection and electroluminescence. Both of those identify defects in the module that are visible, quality concern issues, and identifying any severe transporting issues like broken glass and issues. In addition to this, power measurements are very important at this stage to ensure that the modules that are sent to site are acceptable within the power class that was spec'd. And this sort of testing can occur both at two stages, as modules arrive on site and also after construction has occurred, because that damage that can occur in the installation process can be assessed by a visual inspection and electroluminescence inspection. So let's break down those tests in a bit more detail. So we are looking at the visual inspection test here, which I sometimes say it's the easiest test and the most difficult test, because it's a very non-invasive, quick and cost-effective method to identify issues in the PV module, but it's also very difficult. It can be very challenging to identify all the defects, and it does require skill and experience. But it's actually really very important. It's just not requiring all the fancy equipment and things that make it nice and straightforward. But it's very important to identify issues that can occur in the PV modules. So as I mentioned before, we sort of have a situation where there's two sets of modules. There's the fielded modules that are 10 years old, and then you have the brand new modules. And when you look at them to do a visual inspection, you're actually looking for completely different things. So in a fielded module, you're really looking for signs of degradation and failure. So it's very important to identify a browning that could indicate hotspots or heating. Backsheet delamination is visible. Backsheet degradation is visible in forms, things like chalking, as well as situations like this where the backsheet is actually cracking. So cracking like that in the backsheet compromises the electrical safety of the module, and that can be a severe safety concern. Other things occur, like the backsheet cracking and can result in moisture and water getting into the modules, which corrodes the connectors and degrades the cells further. So when we look at new modules, we're inspecting them for defects that would have occurred in the factory, typically, and then we would, from that point on, assess for any signs of premature or early degradation. So you would look for foreign materials, as well as looking for things like these fingerprints in the cells. Foreign material can be hair, or sometimes poor insects get trapped in there as well. And then what is quite common is, as the technology has changed in PV modules from being a ribbon connector on the bus bar, you now have just a single wire. So it's very common for that wire to go a bit off track or off pad, and that then affects the collection of carriers at that point. So it is a small decrease in efficiency of the cell. Again, as the modules are getting bigger and the spacing is smaller, it is not impossible for the cells to actually touch. So that the clearance between individual cells and the clearance between the frame and the cells is quite important to monitor. And then what is quite a concerning trend at the moment, observation at the moment, is when the glass of glass modules will spontaneously break on installation. It's not super clear in this image, but this is a module where the back sheet has cracked after a short time of installation. So I think much more research is needed into looking at the causes of that sort of defect, as it is quite prevalent all around the world. Okay, so electroluminescence we often refer to as the solar panel X-ray, if you want to put it in the most basic terms, but it's essentially operating the solar cell in reverse. So you're applying a current to the modules, which forces the carriers to be generated in the material. When they recombine, they're emitted in the form of light. And you have a camera with appropriate filters that is just picking up that specific range. And it's very effective in identifying defects in the cells. And these images are very nice and high resolution of individual cells. And they do a very good job of indicating what you can see, how a break in the busbar finger results in an area of decreased light at that point, how the micro cracks that occur in the cells are very prominent as dark lines. And if these micro cracks occur in a way that results in one area of the cell being completely disconnected with no electrical contact, then it will appear dark in the EL image, and that area is then not contributing towards power generation. So as electroluminescence became a more common technique, people saw microcracks more. They identified where it was occurring in the handling of modules, in how modules were packed, and how they were transported. And as it became part of the quality assurance process, it became much easier to identify the causes of these microcracks. And one of the byproducts of that, among other factors, is, I mean, these are older modules with 2 bus bars. Newer modules will all have several bus bars, 8 or 9, and the effect of that is microcracks have much less of an effect on the output of the module, because it's not as easy to result in an electrically disconnected area. So this is quite a severe example of a crack in a new module, but a single line crack would actually have a very limited effect on the performance, and that we would class as an uncritical crack. Newer modules have the similar problem where there can be soldering abnormalities where parts of the cell appear darker. And this, I hope, is clear enough on the screen. This here is what we call a V crack. So it's occurring at the edge of the ribbon. And there is a potential that those cracks can develop and spread with time. So the evaluation of this V crack would take into account the potential for it to grow with time. So this slide here just gives an overview how the EL criteria can be applied. So this is the MBJ module judgment criteria, version 3. 3 and 4 both look at, I would say, the older type of modules, and there the valuation of the cell and the module is very much tied to how much of the area, how much area of the cell is affected and disconnected, as well as taking into account to other EL abnormalities that can have an effect on performance ultimately. So the site acceptance testing can be done in a container or dark room, and again, it can pick up damage that occurred during transportation. In situ EL imaging can be done on ground mount systems without the modules being removed, and this allows defects to be identified without very quickly and on quite large sample sizes. So it's also possible to do EL imaging on rooftop modules. So this is an example of a module that has had quite severe hail damage. And this module appeared completely fine. The glass was not broken. The glass in the module surrounding it, some of the modules had broken glass, and the modules that didn't have broken glass, some of them would look like this. So it's quite very effective in identifying the problems with the module. Okay, so maximum power measurement. So we come to this last because all my case studies are looking at maximum power measurements and how it is the best way to identify the performance of the module. So visual and electroluminescence, you're identifying quality defects, but power measurements, you're getting a measurement of what is the power, what is the actual module outputting. So any solar simulator would have a certain degree of measurement uncertainty. So typically it is about 3% for most PV module. For most solar simulators have about a 3% measurement uncertainty. And it is an important step to monitor the annual degradation of modules. So an initial test would create a baseline, and over the period of operation, every annual testing can indicate how the module is performing based on that initial measurements, and how is the degradation as expected. So when modules are received, a test is very good to give an indication of if it's been overspecified or underspecified. So PV Insight has mobile labs that are available for on-site testing. So this is the newer mobile lab, which is in a trailer, and this is the older one that also is in a contained container system. And this is the newer one. It's now in the trailer. So just briefly, because often it's asked how many modules are required. So the process of how many modules is required to test is based on the AQL system, which is an acceptable quality level. And typically it's defined based on how many modules there are in the entire plant and what level of inspection is required. So things like the flash testing and electroluminescence would be completed on a smaller sample of modules at a special inspection level of 4, for example, and then a test like visual inspection completed on the general inspection level. So this example here is a table from an Indian testing company, and they have put together quite a nice summary of how the testing, the AQL affects testing, and how many modules would you expect to test if there were 10,000 modules during pre-construction. So the way you read one of these tables is you look for, 100,000 modules, so you look for 100,000 modules there, and at S4 level means you would test 80 modules for EL and Flash, and 500 on the general level, general inspection level 3 for visual inspection. So then my case studies that I'd like to present range from utility scale testing down to a residential and off-grid applications. So the first case study I'd like to present, which is quite, I think, a positive story, because it's looking at how module quality is at a utility scale. So in a utility scale, many plants have implemented quite strict quality control processes, which include annual degradation testing programs. So we've been part of working with some of these plants to do this testing for them. And routinely what we see is that these modules will come back every year, that we test the same sample of the same modules every time. And the results show that in these plants, the modules that were provided initially were all underspecified. So it means the initial power was higher than the nominal power. In this case, they were 8% higher. And then after 10 years, the majority of the power, the majority of the modules will still be above that nominal power, and almost all above what the warranty power should be for a 10-year-old module. So this is observed in most large-scale plants where there has been some agreed quality assurance plan. And this is observed internationally as well, that there's an underspecification of modules in the utility scale. This assures from the manufacturer and for everyone involved that performance warranty is met, but it does not prevent product defects from occurring. So there is still product issues that could occur, but certainly the performance of the module is higher than the warranty was allowed for. So the second case study is then looking at the module quality in a commercial environment. So as part of a lab exercise, we purchased modules from local suppliers. They are all tier 1 modules, well regarded brands. All the modules are new. They were different types, different sizes, different brands. And it was a good indication that the point of the exercise was to get a sort of a sample of the modules that were available commercially. So we sort of had that stock of knowing what was happening and being able to test it. All the modules that we purchased, they all had a positive power tolerance, which means that's 0 to 5 watts. There was one, which is this one here, which had ± watts, but they all were supposed to have a positive power tolerance. So the initial power of all these modules when we measured in our lab was lower than the nominal power. The range of these results was from 0.9. The range of results was from negative 1.9% to negative 2.7%. So they were all below the spec. But it's important to note that our measurement uncertainty, like most labs, is 3%. So actually, these modules are acceptable. And there's nothing wrong with them once that measurement uncertainty is taken into account. So this is quite a common problem and a common conclusion. It's not got anything specifically to do with you can't be taking as our lab has gotten different results. It's quite common, and it's observed around the world that modules modules will be lower, so they will be overspecified commercial market. So this drop is equivalent to 1 year of outdoor exposure if you use a 2.5 decrease in the first year. So the last story is, I think, quite an interesting case because it's looking at sort of this probably the smallest end of the market, which would be a residential or an off-grid application, modules that are not coming from a tier 1 or a reputable, a particular, a brand name. So we were approached by a residential PV system owner who had concerns about the performance of their system. We tested a sample of 4 modules, and these were modules that had been rebranded in South Africa, and they'd been installed for 22 months. So the gray bar here is where you would expect the performance to be based on the warranty and the age of the module and the measurement uncertainty. So all the modules had measured, the power measured lower than what was expected given the age of the modules, with the worst of them testing at negative 22% below the nominal power. So these modules are not meeting then the performance requirements given by the warranty. So electroluminescence is very effective in identifying what is the cause of this low performance. So if you just do the power measurements, then maybe the modules were damaged in installation, or maybe there's hail defects or something like that. But by doing EL on these images, on these modules, you can see in the images there are some critical cracks caused by a hailstorm, but they're not significant enough to result in the decreased power. And in fact, that their product manufacturing concerns, things like mismatched cells, solder abnormalities, and accelerated degradation, indicating that the modules in this, the modules have some product defects that is resulting in accelerated degradation. So this is quite a unique in the way that very few people in this, very few people test their modules in a residential sense. So it's possible that it's more prevalent that these modules are underperforming. It is quite common that modules going into sort of camping or those sorts of sectors of the market can be underperforming. Okay, so in conclusion, I feel like I've talked for a long time now. The quality assurance process is very vital for the PV industry, and it's important to ensure the performance of modules, ensure that they perform as expected, and ensure that the reliability is there of the entire lifespan. So you need to have the quality assurance process is there to minimize risk, improve durability, and also ensure that the systems develop on performance, deliver on performance. So once modules are installed in the system, it's very difficult to identify the cause of underperformance. Even IV curve measurements carry a much higher measurement uncertainty. So you cannot 100% pin down whether the module itself is contributing to underperformance once it's installed. So I think South Africa is in a very good position as a country. Not only do we have we are in a very good position as the PV industry grows in South Africa, because not only do we have a very good and strong and active industry association like SAPVIA that's taking its time to organize seminars like this, but we also have 2 accredited PV testing laboratories. So PV Insight, which I've run through now, and also there's the CSIR PV module quality reliability testing laboratory, which is based in Pretoria. And they are able to do all the reliability testing. And the reliability testing is very important because it will give you an indication of the future performance of modules. So quality testing, as we're doing it, indicates how things are at the moment. Is it acceptable at the moment? But the equipment that CSIR has and the procedures that they have in place there are really vital to give you an indication of the future reliability. So testing is key to ensuring quality. I mean, I think South Africa has quite a lot of testing facilities available, probably for a country. We have quite a high capacity to test. And also it has just been shown that quality will improve when testing is included in the process. So the PV industry has changed a lot over the past 10 years, and we're sort of 10 years down a road that is measured. I mean, PV systems, we're talking in 20, 25 years increments. So we're there. And I think I'm going to keep using this metaphor, but there's sort of the role of quality assurance is to sort of look at the road ahead. And is it going to be a potholed road full of challenges that you have to deal with things as problems as you go? Or is it going to be a smooth, easy process as the industry grows and these systems contribute positively to the South African economy and our electricity demands? Okay, great. So then I'll see if there's any questions. Thanks. We'll find the screen again.
Thanks, Jackie. I think just before we take some questions, I just want to thank you and also just give maybe the House quite a number of roll call or House rules. We're gonna just take one speaker at a time. I think we have until 1:30 for us to take on questions. Our attendees also welcome to type them in the chat section. I see we already have quite a few questions there. We will take maybe 1 or 2 questions as you address them, and then we'll move over to other questions, both in written format and also in also just if you turn your mic on. So back over to you, Jackie. I think our attendees at this point should be allowed to have their mics turned on, but preferably if you raise hands, colleagues, it will make it easy for us to take over on this process. Thank you. Over to you, Jackie.
Oh, to me to manage the questions.
Maybe just to answer a few. I do not see any hands at this point. However, I will read 1 or 2 questions as I see the chat section. This question reads as, how much cost is it to set up an accredited testing lab, and what are the requirements? So I think this is a criteria for the testing facility. Maybe that question.
Okay, sure. So how much does it cost to set up a lab? Okay, well, it's very, very expensive. No, look, I mean, the equipment involved is all very expensive. It's very specialized. And so CSIR is set up in Pretoria with the full suite of certification testing equipment, which includes the environmental chambers, the dynamic load testing, and on our side we have the mobile solar simulators. Requirements, both the laboratories are accredited with SANOS, which is the South African National Accreditation body in South Africa, and that in itself is a process. So yes, it is a continual management of both that accreditation and the equipment required.
Thanks for that response, Dr. Shekhar. Hopefully it's helpful. Another question reads from Reynard as, and it says, what is your take on tier 1 modules versus other modules' performance over their lifespan? And maybe just before you answer this one, I would like to just refer this particular colleague to our previous webinar, because we did actually show some results as far as the presentation from CSIR is concerned, comparing, and whether tier 1 modules versus other modules, does it always indicate a high performance? I think that question was perfectly answered there. Perhaps we'll take this question further as well, but you're welcome to just add on your insight as well, Jackie.
Yeah, I mean, one doesn't. I think the tier 1 and that accreditation process is defined by those international quality assurance programs that takes into a whole bunch of factors, from how they produce to the stability of the companies to that. So I think you take it for what it means. I mean, there's independent verification of it, and again, you're looking at a module a product that's supposed to last 20 to 25 years. So I think one can take an expert opinion on that quality for what it is.
Thanks for that response, Jackie. Maybe just to also add onto that question, one of, I think, realizations that one should take on is that a tier 1 or tier 2 up to tier 3, whatever that classification is, it's a commercial classification. It's not necessarily a scientific proven classification as such. So I think it's important to take that in caution, and perhaps from the results as well that I was making reference of earlier, there is a clear distinction and indication that tier 1, for instance, panels are not necessarily high-performing panels. Although in the same category, you can still find very high-performing panels. But yeah, I think that's a very interesting question. Another follow-up question from the first question, Dr. Jackie, is that what about mobile testing trailers? I believe this particular attendee is very interested in knowing the costs there. Thank you.
I'm not selling mobile testing trailers. It would be much more efficient to contact us, and we can advise on what your requirements are for actually testing.
Thank you for that question, or response rather. We've got a question from Tane, which reads as effectiveness on drone and thermal scanning as a quality assurance gate on installation completion and then periodically during operation. I'm not sure if this is a question or a comment rather, but any take on that one, Dr. Jackie?
So on the effectiveness of drones, of thermal drone scans?
Yes.
Yes, so I think all these techniques work in conjunction together very well. So what the advantages for thermal drone scans are is you cover a large area very quickly, cost effectively, minimal, no downtime, and then you can pick up, but what you're only picking up, you're picking up heating defects, so those sorts of issues, and it can be challenging to interpret the results. So it is a great way to review an entire PV plant and identify areas for further testing. And that further testing can be things like IV curves to see what the actual performance of those modules is. It can be the electroluminescence testing. I mean, electroluminescence testing is the test that'll tell you exactly what is wrong with that module. Like, is it cracks? Is it other defects? You know, there's no ambiguity in what happens. So thermal is a great technique, and it works very well with the subsequent testing. That's not possible to do on such a large area. I see
Thank you
there's
with that. We've got a hand up from Aidens. I think I'll just turn their mic on. Oh, I think their mic is already on.
Thanks, moderator. Thanks, Doctor,
Yeah,
for the thanks, Doctor, for the presentation. You talked about something on site acceptance testing, that is sampling. I was just thinking, and there a possibility that you could sample modules which are fine, and you leave out the ones actually which have issues, especially those which have internal damages on the photovoltaic material, and wouldn't that one give an opposite report of the site? That's my question.
Yeah, I mean, that is, sorry, that is always the challenge with any form of sample, is to ensure that it is representative, with at the same time being cost effective and efficient and feasible. So yeah, it is something to consider.
Okay, thanks.
Thank you for that response and the question. Just one or more, two other questions before we close, colleagues. Okay, I'll take it as if we do not have any further questions. Jackie, I'd just like to thank you so much for preparing this presentation with us today, and for your colleagues also just in arrangements. And I would also just like to thank our audience today for joining us. Please do note that this session was recorded, so it will be also shared by every attendee who was present with us here today. And that is it from us as the SAPIA Secretariat. We would like to just thank you so much, colleagues. Have a good afternoon.
Thanks very much, everyone.
Thank you.